In lecture 5, I'm going to introduce something called radiometric correction. Firstly, I'm going to introduce interactions between EMR and atmosphere, and also between EMR and terrain, okay, objects on the ground. And in the second half of this lecture, I'm going to introduce different types of radiometric corrections, including sensor correction, atmospheric correction, and topographic correction. So firstly, I would like to introduce atmospheric energy-matter interactions. So the traveling of EMR is complex. It's not complex when it's in the outer space, but when EMR, solar radiation, so EMR from sun, when EMR arrives at the atmosphere of the Earth, okay, there will be interactions. Okay, as long as EMR is traveling through atmosphere, there is interaction between EMR and the atmosphere. And in general, there are three types of them. The first type is scattering, reflection in an unpredictable manner. Okay, and then there is absorption, which means that atmosphere absorbs part of EMR from the sun, process by which radiation is absorbed and converted to other forms of energy. And there is also transmission, okay, process by which radiation passes through a material. For example, if there is glass, if there is a very thin plastic bag, radiation can go through them, can travel through them, right? So due to this very complex interaction process between EMR and atmosphere, part of the EMR will stay in atmosphere because it can absorb EMR, right? Part of them will be scattered, which means the direction of the EMR will change, which means some of EMR will not arrive at the ground of the Earth, right? Part of them will part of EMR will eventually arrive at the ground, at the surface of the Earth, right? Due to transmission, and it could be reflected by different objects, and then it will have to travel through atmosphere again, and then eventually arrives at the sensor in the sky. So you can say it's not a very relaxed travel, okay? If you are EMR, you get through a lot to get to the ground of the surface of the Earth. Oh, sorry, get to the surface of the Earth and then get back to the sensor. That's why we need what? Atmospheric correction, and it is a part of radiometric correction. So let's go through these different types of interactions, okay? So first, I want to talk about atmospheric scattering. So the direction of, after the scattering process, the direction of the EMR is unpredictable, okay? It could be scattered into different directions. So the type of scattering is a function of wavelength and also the size of gas molecule. So there are different types of scattering, and the type of the scattering is decided the wavelength of the incident radiant energy, or you can say the wavelength of EMR, lambda, and also the size of the gas molecule, dust particle, or water vapor droplet, dP. Okay, when EMR encounters them, there is scattering, right? And their diameter, the size of the gas molecule, decides what type of scattering is going to happen. So essentially, there are three types of scattering. The first one is called Rayleigh scattering. It happens when dP is much smaller than the wavelength of EMR. Rayleigh scattering is the reason why the sky of the Earth is blue. I'm going to introduce that later, okay? So the second type is called mere scattering. It is happening when dp is equal to the wavelength of EMR, not exactly equal to, but dp is very close to the wavelength of EMR. And the third type is called non-selective scattering. It happens when dp is much larger than the wavelength of EMR. I'm going to explain them one by one. Okay, the first type is called Rayleigh scattering. Rayleigh scattering, we also call it molecule scattering, occurs when the diameter of the matter, usually air molecules in atmosphere, they are many times smaller than the wavelength of the incident EMR. And it happens in the atmosphere 2 to 8 kilometers above the ground. Okay, and the strength, or say the amount of scattering, the strength of scattering, or the amount of scattering is inversely related to the force power of the radiation's wavelength. You don't have to memorize this, but when next time when you hear this term, Rayleigh scattering, you should know that this is the reason why the sky of the Earth is blue. Okay, because you know that blue is the light with the shortest wavelength in visible light range, right? And most molecules in atmosphere, they have very small diameter, okay, and they scatter a lot of blue EMR, or blue visible light, on all directions. Okay, that's the reason why we say Earth is that's another story. Earth is a blue planet because of water. But when you're standing on the ground in a sunny day, you say that the sky is very beautiful, is blue. That's because the existence of Rayleigh scattering. Okay. Second type of scattering, mere scattering. Okay, mere scattering takes place where essentially spherical particles present with diameters approximately equal to the wavelength of radiation. Okay, it happens somewhere lower than 4.5 kilometers above the ground, of course. Okay, so for visible light, water vapor, dust in the air, and other particles ranging from a few tenths of a micrometer to several micrometers in diameter are the main scattering agents. Okay, so this is the second type of scattering. And the third type is called non-selective scattering. It happens when particles in the atmosphere is larger, much larger than the wavelengths of EMR. Okay, okay. So all wavelengths of light are scattered by these agents, by these particles with a very large diameter. So the most famous one, and I think this is the most straightforward one to understand, is water droplets. Okay, they are floating in the air, especially after a big rain, right? Water droplets, and in clouds, of course, water droplets scatter all wavelengths of visible light equally well, causing the cloud to appear white. So now you know why the clean sky is blue, and you know why clouds, they are white, because of Rayleigh scattering and non-selective scattering, respectively. Okay, okay. So they besides scattering, there is also absorption effect from atmosphere. Okay, absorption is the process by which radiant energy is absorbed and converted into other forms of energy. The most important other form here is what is thermal energy, right? um, An absorption band is a range of wavelengths in the electromagnetic spectrum within which radiant energy is absorbed by substances such as water, CO2, oxygen, ozone, and uh, nitrous oxide, N2O. Okay, the cumulative effect of the absorption by the various constituents can cause the atmosphere to close down in certain regions of the spectrum. What does it mean? It means that since atmosphere is absorbing part of EMR, only the other part of the EMR that was not observed by atmosphere can arrive at the surface of the Earth. And this is a huge problem for remote sensing, because if the EMR cannot arrive, cannot get to the ground of the Earth, how can I collect reflected energy? Right? If all energy has been absorbed by atmosphere, there is no energy arriving at the surface of the Earth. Fortunately, that is not the case because atmosphere of the Earth only absorb part of EMR from the sun. And here is a figure to show you that. You can say here we have a huge figure showing you different how can I say that? Different windows, absorption windows for different gases. Okay, so we have N2O, we have oxygen and O3, ozone, right? We have carbon dioxide, CO2, we have H2O, which is water, right? So the horizontal axis here is wavelengths from 0.1 micrometer to 30 micrometer. Okay, and the vertical axis is for absorption. It's a percentage value. So for N2O, you can say it's from 0 to 1. For ozone and oxygen, it's also from 0 to 1. Obviously, the larger the value, the stronger that gas, the stronger the absorption ability of that gas. Okay, so for CO2, for HO2, different gases, they are main gases in Earth's atmosphere, right? They have different preferences on absorption EMR. For example, CO2 does not absorb any EMR with wavelengths shorter than this specific value. It's around 1.5 micrometer. So CO2 is actually very friendly to visible light. It does not absorb any visible light and near infrared light, or say near infrared is not light. Let's call it near infrared EMR. But beyond near infrared, CO2 absorbs a lot of energy, especially around here. 2.8 micrometer and above, which means that if your EMR is with this range, and with this range, CO2 will absorb most of them. And what is this range? These two peaks, they are within thermal infrared range, which means that they have a lot of thermal energy. So now you know why CO2 is the main enemy of global climate change. Because CO2 has strong ability to absorb something called thermal energy, which will lead to a higher atmospheric temperature. So that's the reason why most countries around the world, they're trying to decrease the charge, the release of CO2 into atmosphere, because it is so good to make this planet warmer. Okay, so similarly, we have the absorption. Say, let's just call this a absorption spectrum, right? Different gases, they have different spectra here. So if you overlap them, for atmosphere as a whole, you can say that, okay, it's not very friendly to EMR. So most EMR with a wavelength smaller than 0.3 micrometer is absorbed by who? By O2 and O3. and the rest of them, they're basically absorbed. And there are only small windows here, invisible light, and here infrared, 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 this blank part. They are EMR who can travel safely to the ground of the Earth, because most gases in atmosphere do not absorb them. Okay? Parts of the spectrum that transmit energy efficiently or effectively are called atmospheric windows. So when you are designing remote sensing sensors, you have to make sure that these sensors, they are sensitive to EMR within this so-called atmospheric windows, or the part of EMR, or in other words, the part of EMR that is not observed by atmosphere. Because if your sensor is very sensitive to the EMR with a wavelength smaller than 0.3, it's meaningless. You can barely collect any energy from the surface of the Earth, because this part of the energy has been observed by O2 and O3 in the atmosphere even before they could arrive at the surface of the Earth, right? So the concept of atmospheric windows is pretty important. It is where you should focus on EMR spectrum when we're talking about remote sensing, because they are just like literally windows, windows opening to the outer space, opening to EMR. Okay, any energy outside of these windows, they're actually basically have been observed by atmosphere. Okay, so absorption. And since we're talking about different interactions between EMR and atmosphere of the Earth, there are two terms you should know. Okay, so they are used to measure, to quantify radioactive energy. Okay, the first one is called IRradiance. It is used to address radiant flux density. So the amount of radiant flux intercepted divided by the area of the plane surface is the average radiant flux density. This is irradiance. Put it simple, okay? Put it simple. Irradiance is the energy arrives at or leaves the surface divided by the area of that surface. So energy per area is irradiance. But if we give a even more strict concept to irradiance, irradiance is a measure of the amount of radiant flux incident upon a surface per unit area in watts. So it is used to address the energy arrives at a specific surface. Excidence is the opposite of irradiance, is a measure of the amount of radiant flux leaving a surface per unit area. So the foundation of these two concepts is the same, is energy per unit area. But irradiance is used to address the energy arrives or arriving at the surface. Excidence is for the energy leaving the surface, okay? And beyond that, irradiance is not good enough, because when we're using a sensor to look at, to collect the surface, reflected surface energy, it can only collect the energy from some directions, but not all energies for all directions. So one more step beyond radiant flux density irradiance is something called radiance. We're only interested in the radiant flux in certain wavelengths leaving the projected source area within a certain direction and solid angle. It makes sense, right? When you are using a cell phone or any camera or remote sensing sensor in the sky to observe a specific area on the ground, it can only cover a small area on the ground instead of the whole Earth's surface, right? Which means that some reflected energy it's not my business. I can only collect energy reflected on a specific direction or directions. So so the energy per unit area on the ground is not good enough. We want something called a radiance. It's the radiant flux per unit solid angle leaving an extended surface, leaving an extended source in a given direction per unit. Projected source energy, a projected source area in that direction. So a radiance is irradiance per solid angle. So irradiance is the energy per unit area. Radiance is irradiance per unit angle. Okay, and angle here is used to address direction. Like I said, when you're using a camera, there is always something called FOV, field of view, which means this camera, this sensor can only cover a specific area, which means it can only collect EMR from a specific direction, right? EMR outside of that direction is something you should not consider because it's outside of your FOV, and radiance is used to address energy per solid angle or per direction, say that. Okay, so you don't have to memorize how, or you don't have to know how to calculate them in this class, but you should know the concept, radiance and irradiance. Okay, so this is the first part of lecture 5. I'll see you in the next video. Okay, thank you.